Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. To your younger brothers and sisters who would want to take up engineering in the future, and to your relatives. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Hello, students, subscribers, viewers, and future engineers. Here are another problems in calculus about uh, derivative interpreted as instantaneous velocity or rate of change. So here are the problems. By the way, if you want to anticipate the solutions to these problems, you can by pausing the video and not looking at the solutions presented here. If a ball is thrown into the air with a velocity of 40 feet per second, its height in feet after t seconds is given by y equals 40t minus 16t squared. Find the velocity when t is 2 seconds. So for part 1, velocity is derivative of y with respect to t, so it is just 40 minus 16 times derivative of t squared, which is 2t, simplifying v equals dy dt equals 40 minus 32t. So the given time is 2 seconds. So 40 minus 32 times 2 is negative 64 feet per second. So meaning to say the ball is falling after 4 seconds. 2 seconds rather. Then problem 2. If an arrow is shot upward on the moon with a velocity of 58 meters per second, its height in meters after t seconds is given by h equals 58t minus 0.83 t squared. Find the velocity of the arrow after 1 second. Find the velocity of the arrow when t is a, and when will the arrow hit the moon? With what velocity will the arrow hit the moon? So for part A, we simply differentiate h with respect to time. So v equals dh dt, and it is equal to 58 minus 0.83 times 2t. Simplifying, v is 58 minus 1.66t. When time is 1 second, substitute t is 1. 58 minus 1.66 times 1, so 56.34 meters per second. For part B, when the velocity find the velocity when the r of the arrow when t is a. We just replace t by a. So it is 58 minus 1.66 a meters per second. Then for part C, when will the arrow hit the moon? So it is projected upward and it will go back after it reaches the highest point. So the arrow will hit the moon when h is 0, when it is again 0. So from the formula h equals 5080 minus 0.83 t squared, we equate it to 0 and we factor out t. So we have t times quantity 58 minus 0.83 t. So there are two times where h is 0. One is when at the start, of course, because the arrow is at the moon surface at the start. So that's why t is 0, but that's not the time we wish or we expect. Time is the other one. Equate 58 minus 0.83 t to 0, so t is 58 over 0.83, and that's 69.88 seconds. Then 2D, with what velocity will the arrow hit the moon? The velocity should be negative, so that means it is now dropping, showing that the arrow is now going back to the moon surface. And 58 minus 1.66 times 69.88 is negative 58 meters per second. Remember the principle, without neglecting a resistance or other resistances, the speed at the same level is the same. So at the start, it is pointed upward 58 meters per second. When it goes back to its destination, it is now 58 meters per second, but going downward, revealed by these results here. Problem 3, the displacement in meters of a particle moving in a straight line is given by the equation of motion s equals 4t cubed plus 6t plus 2, where t is measured in seconds. Find the velocity of the particle at times t equals a, t is 1, t is 2, t is 3. So we differentiate the equation s with respect to time, and that is interpreted as the instantaneous velocity of the particle at any time. So s is 4t cubed plus 6t plus 2, so v ds dt 4 times 3t squared plus 6. Simplifying, it is 12t squared plus 6. When time is a, we just replace t is a. So for 3 part 1, it is 12a squared plus 6 meters per second. When t is 1, substitute t is 1, 12 times 1 squared plus 6, so it is 18 meters per second. When t is 2, 12 times 2 squared plus 6, so 54 meters per second. When t is 3, 12 times 3 squared plus 6, so it is 114 meters per second. Then problem 4, the number n in capital N in thousands of cellular phone subscribers in the Philippines is shown in the table. Mid-year estimates are given. So this is the table. Find the average rate of growth, part I, from 1995 to 1997. So from 1995 to 1997, 2,461,000 subscribers minus 873,000 subscribers divided by 2, where 2 is the difference between the period 1997 and 1995 in years. So 2461 for part I, the average rate of growth is delta n over delta t. So 2461 minus 873, remember these are in thousands, divided by 2 years. So delta n over delta t, the average growth rate for those periods 1995 to 1997 in 1,000 subscribers is 794,000 subscribers per year. Then in part 2, 1994 to 1995, so these are the data, 873,000 minus 572. Sorry, 1995 to 1996. So 13,000 minus 873,000 divided by 1 year, 1995 minus 1996, 1 year. So that's 640,000 subscribers per year. Then part 3, 1994 to 1995, so 873,000 minus 572,000 divided by 1 year again between 1994 and 1995, so 301,000 subscribers per year. So the units subscribers in 1,000 subscribers per year. Then 4B, estimate the average rate of growth in 1995 by taking the average of two average rates of change. What are its units? So it should be the average growth rate here between 1994 and 1995 and between 1995 and 1996. So it is one half quantity between 1995 and 96. This was the average growth rate, 640,000 subscribers per year. Then between 1994 and 95, 301,000 subscribers per year. So it is the average growth rate in 1995 is 470.5 thousand subscribers per year. Then 4C, estimate the instantaneous rate of growth in 1995 by measuring the slope of the tangent. So for part 4C, we have to plot the points. So let's have this graph here. And anyway, these are also divided so that we can estimate it closely. So in 1993, we have 304.5 thousand. So that's the value. 1994, we have 572,000. So that's accurate. 1995, but the graduation is small. 1995, 873,000. 1996, we have 13,000. Then 1997, we have 2461,000. So we have to draw uh, the tangent at this point here. Then this is estimated to be uh, 1,340,000 subscribers there. And here at the lower part, 480,000 subscribers. So therefore, the slope of this tangent line, that's the slope, this tangent line, is 1340,000 minus 480,000. And because this is between 1994 and 1996, the time is 2 years. So divided by 2, so the average DNDT is 430,000 subscribers per year. So take note that your answer may be different a little from here because it depends on the estimate of the slope of this tangent line. So you just get the vertical distance divided by horizontal, which is in years. So that's it for this video. I hope that you were able, for those who are attempting to solve these problems, you are able to get the same answers as here, except for 4C maybe. You may have 425 or 435. Within that range, that's fine.